Hey everybody, welcome back. Today we've got an interesting one that was sent in. This is a company I haven't really heard about. I don't know if it's a relatively new company. It's definitely new to us. This is the Falcon F200 model, and there's a lot of good here. A lot of good, but then there's still some room for improvement. I've got a lot of mixed feelings about this one. There's a lot of questions in my mind regarding this design and what was done with it. There's a few head scratchers. So for you guys out there from this company, if you are from this company and you've got some information for me about some of the questions that I have about this design, feel free to drop them into the comments section. Now, let's dive into this thing. And first I'm going to start with the cabinet. The cabinet of this thing looks really nice. I mean, the veneer, the quality of the work on it looks great, and I don't know if you can tell, but it's kind of slanted in. It's got one shape kind of like this, and it just looks beautiful all over. I love it. The binding posts on the back are high mass. I'm not a big fan of the high mass binding posts, but it is pretty well built. It's got a thick front baffle that feels like it's at least an inch thick, and the rest of it feels like 3/4 inch, and there's a brace here. So it's not something that's out there going to make tons of noise and rattling and resonating. They built it fairly well. Also, inside of the woofer through hole, they didn't radius it, but they chamfered it. So imagine the through hole goes through, and then at the back, it's got a chamfer on it. So they've done away with that diffraction issue that is typical when you slam a woofer into an inch thick baffle. You don't want that radius on the back. They took care of that. Driver quality is pretty nice on this thing. I mean, nice. The RM Cantus drivers are what's used in this thing throughout. It's the big RM Cantus 4-inch ribbon tweeter, and that has its pros and cons. 100 dB sensitivity or more on this tweeter, so it can play. The thing I don't like about tweeters, when they start getting taller than 3 inches, the vertical dispersion starts becoming more and more limited. The 6-inch diameter versions have a very limited vertical range, so you have to be seated right within that range to hear the highs. As soon as you get above and below it, the highs fall off. And this one's kind of in between. 4 inches tall is a little on the tall side, so you still have to be seated in order to hear that high frequency. As soon as you stand up, the highs do drop right out of it, and we'll see that in the measurements. The woofer, pretty nice little woofer. Cast frame, big motor structure, big vented pole piece, and I had to look up some information on this thing to see what this comb material was, because it has a nice feel. I can tell by feeling of the comb material how well it's internally damped. In other words, if you thump on this thing, it doesn't transmit a ring through the rest of the material. It's more like, imagine thumping up against a sandbag versus thumping against a piece of wood versus thumping against a anvil. You know, there's always a different resonance and a different ring to those properties, and I could tell this had a very natural feel. According to what's online that I could find on this was some type of a carbon fiber combination material, but I don't see any woven carbon fiber through it at all. It really has kind of a paper textured feel to it, and it was pretty well behaved. It has a rising response, and it's got some stuff going on way up top, but it's got a reasonable usable range on this thing. It's got a pretty good little X-Max on it, 6 millimeters each way. The thing that kind of threw up a red flag, though, was it has really low QTS. I mean, it wants to be in a small box. In fact, the total QTS on this thing was 0.19, which means as a ported box, it only needs 0.158 cubic feet. So 15% of a cubic foot is all the airspace it wants in a ported box. To be part of the suspension and part of the compliance, it needs that airspace behind it. Unfortunately, I realized pretty quickly that is not how big the cabinet is. So I modeled the cabinet with this woofer in it, and what it does is it has, on the low frequency range, instead of it just coming flat out and rolling off, it has what's called an extended base shelf, where it drops off starting around 100 hertz or so, and it levels out longer and then drops off. But it gives up sensitivity to do that. So instead of being up here at 90 dB it drops down to 84, 85 dB, and it extends it longer and then drops off. Now, in my measurements, I'm only measuring it to 200 because that's all I need to see. What's going on below that, I can't change. That's not a variable. It's fixed. So whatever it's doing, whether I'm doing an upgrade on it or not, there's no way for me to change that when we're doing an upgrade on a speaker. So I usually don't look at that at all. Sometimes when we're working with different speakers, that especially our own designs, we look at in-room responses and we look at different things to see what the low end is doing. We'll take near-field measurements. We'll take measurements of the port. We'll move the mic further away and take measurements further away that's still gated so that we can see a little lower. There's things that we do when we're looking at it, but when we're looking at it like that, it's because we have the ability to change it in our alternate and we're tuning it. In this case, I don't, so it doesn't really matter. So this speaker is going to work out better if you placed it near a wall. If you got some bass or some port coupling with the rear wall, it's going to bring some of that back up, and it may be what you need with this speaker. Otherwise, it may be a little thin on bottom. Now, guys over at FICO, if that's not correct in some way, if there's some additional information you want to give me on this as to why you put this in 0.7 cubic feet of airspace, which is a lot more airspace than is required, over 3 times as much airspace, you can drop some of that information in the comments section. Now, let's go back to those binding posts. I don't like a heavy mass binding post. In other words, something that's a lot of metal, a big chunk of brass or copper. I don't know if these are brass or copper, but they're one of the two. They're not ferrous, and they did put a non-ferrous nut on the inside holding it on. However, they put a steel washer in between to sandwich it in there to tighten it down on. I'm thinking, you were this close. You almost had it, and now you got that binding post going through a big ferrous material that, as we've talked about in the past, it's going to hold some residual charge, and it does affect the signal. It would have been great if you'd used a little nylon washer or something else there, that type of material, rather than a steel nut. The other questions I had really revolve around the crossover, and there was something interesting in this crossover. Let's look at it first and just take a look at what's here. It's got a big iron core inductor on the woofer. It is a laminated iron core, but it's not an air core inductor. It's like, oh, why did you do that? You were this close. Because the rest of these parts are not bad at all. And then you did that. And typically when we're doing speakers, we never want to put anything that's going to hold a residual charge in a circuit to where it's going to be playing above the vocal region or into the vocal region. Because these do cause some smearing. No big deal if it's playing 200 hertz and below. At those frequencies, it's hard to hear any slight residual charge that it may have imparted onto wavelengths that are really long. When you start getting up in the vocal region, you start hearing differences in clarity when you go from an air core to an iron core. So you were this close. Little iron core inductors, one on the tweeter circuit, and they have some Mundorf caps on here. And the Mundorf caps are pretty decent caps. I'm not a big fan myself, but they're not bad. They're better than the Chinese budget caps you see out there in almost everything else these days. What's puzzling is they used a 400 volt rated cap tacked onto a 800 volt, I think a 600 volt or 800 volt rated cap. Let me look at it again. Yeah, 800 volt. There's a 400 volt and an 800 volt, a 3.3 and a 3.3 to make a 6.6 out of 2 dissimilar caps in 2 different places. And when you use a bigger value cap, its discharge rate is slower. And when you use 2 caps the same value like that, a 3.3 and a 3.3, one of them's dissipation rate is faster than the other, and so the audible effect is a little bit of smearing. Imagine one cap is holding the charge and releasing it, and the other one's holding the charge and releasing it. It kind of works like that. Not a good idea. Also, why use high voltage rated caps in a speaker crossover? That doesn't make any sense. Unless you're putting thousands of watts through there, it makes no sense to do that. Reason being is on high voltage rated caps, the film is a lot thicker. So imagine a conductive material sprayed onto a film substrate, and then it's rolled into a circle, And the film is what separates one layer from the other layer. So the thicker the film is, the higher the power handling it has. In other words, it takes more power to short through that film and to arc through it. So it's got a higher power rating. However, the thicker film doesn't sound as good. If you can make that capacitor smaller and you can make that film thinner, it's easier for that signal to pass through there in a way, and it has a better sound to it typically. When you get into the bigger ones, the film's thicker, so now the cap has to be physically bigger in order to get the same value. You have to increase the surface area because you've made the film thicker. So you lose some sound quality when you do that. Usually when you use caps of this voltage rating, you're using it in an amplifier circuit or power circuit where you need high voltage, not typically in a speaker circuit. So I'm puzzled by that. The other thing is, right here there is a little LCR network. An LCR network is a resistor, a capacitor, and an inductor. And we use circuits like that as notch filters or impedance traps where we have a crossover and it has a huge impedance rise. We'll go in and put a circuit like that in there to bring the impedance down so the amplifier sees an even load. In this case, there was one of those on the circuit, which is weird because the actual crossover didn't cause a big impedance rise. So why would that be on there is kind of what I'm questioning. And instead of just jumping it across one of the binding posts, it went from the positive on the woofer binding post to the negative on the tweeter on these binding posts. So it's connecting these together, which if you're using one amplifier, it's going to work the same either way, whether you go from positive to negative on the woofer or the tweeter because it's at the front of the network. Or if you jumped it from the positive on the woofer to the negative on it acts the same. However, if a person were trying to bi-amp these and put an amplifier on each one, those amplifiers would be connected through that LCR network, which I don't know how well some of the amplifiers are going to like being connected at the same time to another amp through a resistive circuit like that. So I wonder what they're thinking on that. So guys from FICO, if you got a little something you want to add as to why you're doing that, I'd be real interested to know that. Also, bi-amping a speaker like this doesn't make a lot of sense. The real way to bi-amp is to take a speaker like this and remove the lows from this thing. Remove the first octave or the first octave and a half. And now your woofer doesn't see those long excursions. It's not trying to do this at the same time it's trying to do this. And it's going to increase the headroom of your amplifier. It's going to sound better. Everything about it's going to be better. And then you can send that low frequency signal to a subwoofer. That's the way to bi-amp. Splitting the woofer signal from the tweeter signal isn't really changing much. Unless you've got a woofer that's got a huge voice coil, which this actually has a pretty good sized voice coil, and it's going through huge excursions and it's creating a big back EMF. There's some advantages to getting your other drivers off of that amplifier because it's creating a back EMF that the amplifier then sees and has to deal with. But when you've got a small woofer like this, typically, the best thing you can do is just knock the bottom end out of it. That's the best way to bi-amp. So I don't understand what's going on here with the circuit that they've strung across that there. That just did not make any sense. Now, let's look at the measurements. Remember I said I'm kind of torn on this one. It's got good drivers, it's got a nice cabinet, and the parts quality is fair. But it measures pretty well also. Let's take a look at the measurements on this thing. Let's start with the on-axis frequency response on this thing. Fairly well behaved. We're within plus or minus 2.5 dB from end to end, so that's good. That's well within an industry standard. It's a little choppy. The top end has got a little hump on it. The woofer's response has got a little bit of ringing up top, but not very much. It's in a very acceptable range. In fact, look at the crossover response where this woofer is crossing to the tweeter and it's crossing just below 2 kHz, right at 2 kHz. But the tweeter's played back pretty far and the woofer's allowed to go up pretty far. So that can be some issues when you start moving up vertically, up and down. Spectral decay looks really clean. Again, right at the top of the woofer's response, up there, right around 2500 hertz or so. There's a little bit of ring going on there, but not that much. Not enough to freak out over. The impedance looks good. It's balanced all the way across. Tuning is at 39 hertz. and it drops to 6.9 ohms. So all that looks absolutely fine. It had a grill, I think, that we tried on and off. The effect of the grill was a little rough. You can see the effect of the grill on this measurement. And then looking at the horizontal off-axis, it looks fairly smooth. It's dropping off real well. It's still a little proud in that 2K to 3K hertz region. It doesn't drop off so much there, but overall, really good in the horizontal. Now, vertical is where things change. When you stand up in front of this thing, the highs drop out of it. You can see in the vertical off-axis, the top end takes a pretty big hit as we start moving up just 4 inches at a time. And a little bit of a dipped area there around 2K, but overall not too bad. It measures pretty well. At first I thought, let's just map out the crossover, don't change anything, offer it with higher quality parts, get some of these big binding posts out of the signal path, put some tube connectors in there, put some good wiring in there, call it good. Speaking of wiring, before I move on, they used good wiring in this thing. It's copper wire, and it is with a nylon dielectric material, which I like. Nylon is a lot better dielectric material than the PVC, and they used pretty good wire on this thing. So I give them a thumbs up there. I don't like, though, that after the nylon wire here, they slid a big PVC sleeve over the whole thing. It's like, guys, you were almost there. It's like you had this wire that's good quality wire. All you had to do is just twist it all the way up and leave it just like it is. It would have been good. The twisting would have rejected RF noise and things like that. But instead you put a PVC coating on it, which is not a good material to have coating the wire. So again, mixed feelings about this one. It's like, guys, you're almost there. You've got great drivers. You've got a nice box. There's just a few details you need to cover, and you've got a great product. So I was going to replicate the crossover, but I got to looking at it and thinking, this circuit here, that doesn't make any sense. That should not be in there. And two, it was a little lumpy, and the top end had a little bit of a peak there at the top, and I thought, it's just as easy to wire these drivers out the port. Let me put a crossover on it and see if I can smooth things out a little bit. Also, I know this tweeter will play down a lot lower than it's playing. I mean, you could cross this thing at 1200 hertz or so, no problem. So I knew there was some performance left on the table there. They were crossing it pretty high for what that tweeter can do. So I thought, let's look at it. And so let's look at what I came up with. New on-axis response, it's a little bit smoother. It's a little bit smoother overall. And I added a little something to bring that top end down because it had quite a little peak up there. And then let's look at the crossover response. I crossed it at about 1550, 1600 hertz or so, right in that range. And if you look at, let's look at the old crossover response compared to the new crossover response. And you can see I'm actually not letting the tweeter play down much lower than it was. If you look at what's going on at 1K hertz, we've not moved the tweeter's response very far. What I've done, though, is I've kept it flatter longer and then let it drop off. So it's not playing so, like I said, that much lower, but we're keeping it flatter longer and then dropping it off. And then we pulled the woofer's response back a little bit to match it. So in other words, we're handing the faster, higher frequencies off to the tweeter a little quicker. We're relieving the woofer of having to do it. That's going to improve clarity and detail. It's also going to improve things in the vertical off-axis because we're crossing it a little bit lower in frequency. So I did that. Let's look at 10 degrees off-axis, by the way, was really smooth. Let's throw that up there and look at how smooth it is. 10 degrees off-axis now. And the impedance curve on it is very similar to what it was. And we're dropping now to 7.3 ohms. And the tuning frequency, again, it showed it right at about 38 hertz. The spectral decay is slightly cleaner than it was, but not by a lot. It still looks very smooth. It was very smooth before. All that's good. Let's look at, let's actually look at the driver responses. I forgot about this one. Let's look at the woofer's response and then the tweeter's response. And you can see they're a little bit rough. The tweeter's response, as you can see, I pulled it way down. I just needed to pull it down so that it wasn't blown off the page because it was actually at 100 dB, which meant if I left it at the scale of the woofer, it would be off the page. So I just pulled it down and printed it, or pulled it down and just saved a JPEG just to see what the actual curve looks like. And it does have quite a knee down there at 1 kHz, so it will go down pretty low, but it had a dipped area there around 2500 that needed a little help there to correct. The woofer's response in this box was not a smooth response. It had a big hump right up there around 1200 hertz. So I thought, okay, this is going to be a little tricky, so I pulled it back a little further with the crossover point, and that helped. And I was able to do that without putting a lot of parts on it. So that was good. Then looking at the horizontal off-axis, again, it's fine. It's still a little proud there in the 2 to 3 kHz region, kind of like it was. And the vertical off-axis, as you look at it, because of the lower crossover point, it's better at the transition between the two drivers. It stays consistent. In other words, it's in phase over a wider range, which is going to improve the imaging and soundstage layering and things like that, because it's more even in all directions. The top still drops off pretty aggressively, though. There's no fixing that because of the height of the tweeter. So that's it on as far as what I did. I came up with a slightly altered crossover. It's not too different. The order and the filter and everything is very similar to what it was originally. I've just tweaked the values and smoothed it out a little bit and let the tweeter play down a little bit lower. So we're going to have a little upgrade kit that's going to have all air core inductors, much bigger, big air core inductor for this woofer. We get that laminated I-core out of the signal path. Sonic caps in the tweeter circuit, a JB cap in the woofer circuit, and some good quality resistors, which they use good quality resistors on this, by the way. They didn't use little cheap sandcast resistors. And we're going to use some of our 4/9 pure copper wire and polyethylene, which is a step up above this stuff that they've got on here, which I like the dielectric material. They just hadn't coated this. And then the tweeter needs some little eyelets on it. You may have to find you some eyelets. I wouldn't reuse these, and these are 10. But this back of the tweeter has those posts on it that you have to actually put an eyelet on and screw it down. It doesn't have something you can solder to unless you make some type of a copper eyelet popping off of it that you can solder to. If you can find a little copper eyelet or something, that'd be great. We don't stock that stuff. So I'd recommend that. Tube connectors, of course, are going to replace one of these sets of binding posts. I recommend running everything to one set. And we're going to throw in a sheet of no-res on this, I think. Yeah, one sheet of no-res also. And all the parts with the tube connectors, new wiring, and a sheet of no-res comes to $519. So it's not that much of an upgrade cost considering what these actually sell for. I can't remember what it listed for, but it's up there in price. But again, I'm kind of teetering on this one. There's a lot of good and a lot of good things that went into this one, but they needed just a little bit more to get it over the edge. Like a little bit better parts quality, a little bit more thought at every little place in the path. You know, keeping stuff like steel nuts or steel washers off of the binding post, things like that. It's like, you are almost there, guys, almost there. So that's it for this one. I hope you enjoyed what we go through as far as upgrading this stuff. I hope it's interesting for you. Hit the subscribe button if you haven't. We do appreciate the subscribers going up, and we'll do some more of these as they come in. I've got more speakers lined up, so hang on. New stuff is coming, and we'll see you guys in the next video.